Hello everyone, I am Dr. P. Kumari, working as Associate Professor in Department of Mathematics, Institute of Aeronautical Engineering. Today I want to discuss some of the problems based on the Green's theorem. So here we are going to know what type of problems they will give to use the Green's theorem. Here two types of problems will be there. Applying Green's theorem. By applying Green's theorem, we can evaluate the integral value, and second one is we can use the Green's theorem to evaluate the integral, and one more model is there, that is verification. So verify the Green's theorem. So these three types of problems we are going to discuss now. So first of all, we should know about the what is the statement or definition of the Green's theorem. Let R be a simply connected region with a piecewise smooth curve is there, that is C, oriented clockwise. If M and N have the continuous partial derivative in an open region containing R, then integral m dx plus n dy equal to double integral R dou n by dou x minus dou m by dou y into dA. So here sometimes in some of the textbooks they denoted like this, p into dx plus q into dy. So in place of m and n, here we are having capital P and capital Q. So double integral over R dou n means here dou q by dou x minus here dou p by dou y into dA means dx dy. So this is one of the formula, and sometimes they will denote like this with the pi and psi also. So we can use any formula with the capital letters M and N also we can indicate, and P and Q also we can indicate, and we can indicate with the pi and psi also. So what is the formula we are using, but we should know about the what is the functions we are going to take for the partial derivatives. So see the problem now. Verify Green's theorem in the plane. So what we have to calculate here, integral over C xy plus y square into dx plus x square into dy, where C is the closed curve of the region bounded by y equal to x and y equal to x square. So what they are asking in the question here, we have to verify the Green's theorem in the plane. So that means first we have to evaluate this integral, we have to confirm that one according to the statement. So C is the closed curve of the region bounded by 2 cos here y equal to x and y equal to x square. Here first of all we are writing the given data. So given C is closed curve. C is closed curve of the region bounded by y equal to x and y equal to x square. Y equal to x and y equal to x square. So what is the y equal to x? What is the y equal to x square? We are going to see here in the figure. So first we are taking here x axis and y axis. So y equal to mx already we know. This is the straight line passing through the origin. So based on this m value, if you are taking m equal to 1, this is y equal to x. That's why we are taking here y equal to x. This is the line. So this is the line passing through the origin. This is y equal to x. Next, y equal to x square. Y equal to x square. So this one we are taking here. So y equal to x square. Otherwise, we can take x square equal to 4ay parabola, we know, right? So that curve. So here y equal to x square, in place of constant we are having 1. So it will be like this. So here this is the region. This is the region. So bounded by y equal to x, and this is the y equal to x square. Here starting point is origin 0, 0, and here intersecting point 1, 1. How we know? So from these values we are going to know about the intersection point now. here y equal to x and y equal to x square. So here y equal to x, y equal to x square means x square equal to x. We are writing here x square minus x equal to 0. We are taking the x common, x minus 1 equal to 0. So x equal to 0, so x equal to 1. So if x equal to 0, what is the y value? So y equal to 0. So here x equal to 1, what is the y value? Y is 1. So here we are getting the points 0, 0 and 1, 1. So 0, 0 is here and here it is 1, 1. So here we got these values. These values are very important because we are going to evaluate the integral by using the limits of these values. So now you know what are the 0, 0 and what are the 1, 1. So based on these points, we are going to calculate the value. So here, what is the verification means? First, we have to calculate along the curve, and after that, we have to calculate for the surface integral also. Why we need to calculate along the curve and surface integral? So first of all, what is the statement of the Green's theorem? What is the statement of the Green's theorem here? Integral m dx plus n dy is equal to double integral dou n by dou x and minus dou m by dou y. Here you can see dou n by dou x minus dou m by dou y into dA or nothing but dx dy. So here this is the LHS part. This is the LHS part and this is the RHS part. So we can calculate the value for the any one value for the applying Green's theorem. But what they are asking in the question, they are asking it to verify the Green's theorem. That means you have to show LHS equal to RHS. LHS equal to RHS. That means we have to evaluate the line integral also and we have to evaluate the surface integral also. Then these two values should be equal. That means LHS equal to RHS. LHS equal to RHS. If you proved LHS equal to RHS, then Green's theorem is verified. This is the procedure we are going to follow to solve the problem. So that's why first I am calculating along the curve. So this is the first I am going to calculate along the curve. This is the LHS part. Here along y equal to x square. So here y equal to x square is this one, right? So first I am calculating along this curve C1. After that along the curve C2. Then total area I can get. So first I am calculating along the curve C1. What is along the curve C1? That is y equal to x square. So here this curve is starting from 0, 0 to here ending 1, 1. So that's why along curve y equal to x square from 0, 0 to 1, 1, the line integral equals 2. So what is the line integral value? Integral here starting value xy and xy. Here x limits also 0 to 1 and y limits also 0 to 1. Y limits also 0 to 1. Now here integral 0 to 1. So here what is the integral value? So you can observe here what we have to evaluate. Integral xy plus y square into dx plus x square into dy. So what is the x value here? Here. So same as it is. Now what is the y value? Y is equal to x square. I am replacing here. So first see here integral over c x into here y is x square. So I am replacing x square plus y square. Y square means x square whole square. X square whole square into dx plus x square into dy value. What is the dy value? If y equal to x square, what about the dy? Dy equal to 2x into dx. That value I am going to replace here. So x square into 2x into dx. So that is only there out here. X into x square plus x square whole square is x power 4 into dx plus x square into 2x dx. Now we are going to simplify this one integral. So how we wrote these limits 0 to 1? So just now I told you here the point is from 0, 0 to 1, 1. So based on this I can say that x limits are 0 to 1. So now integral 0 to 1 x into x square is x cube dx plus x power 4 dx plus here x square into 2x. So this is 2x cube dx. So then x cube dx plus 2x cube dx is 3x cube dx plus x power 4 into dx. Now, so here integral 0 to 1 x cube dx plus 2x cube dx, that is 3x cube dx plus here x power 4 dx. Now I am taking constant out 3 integral 0 to 1 x cube dx plus integral x power 4 dx. Now we know the integration formulas, right? What are the integration formulas? Integral x power n into dx is equal to x power n plus 1 by n plus 1. So here 3 integral x cube is here x power 4 by 4 plus here integral x power 4 is x power 5 by 5. Now limits are 0 to 1. So here 0 to 1 to 0 to 1. Now we are going to simplify that value, that is 3 by 4 x power 4 is 1 minus 0 plus here 1 by 5. So 1 minus 0. So finally I got here this is 3 by 4 plus 1 by 5. 3 by 4, 1 by 5. What is the simplification here? 4 5s are 20. So 5 3s are 15 plus 4. So this is equal to 19 by 20. 19 by 20. So the value of the integral along the curve y equal to x square is 19 by 20. So first part is calculated, that is integral xy plus y square into dx plus x square into dy along y equal to x square, along y equal to x square is equal to 19 by 20. 19 by 20. That means only one curve is completed. That means this curve is completed. Now I am going to calculate along this curve. Then I can add these two to get the total integral value. So that's why I am taking this one as a C1. So first value integral along C1. So the xy plus x square into dx plus x square into dy value is 19 by 20. This is already calculated in the along the curve C1. Now I am going to calculate along the curve C2. So here C1 curve is started from 0, 0 to ended here 1, 1. Now I am going to calculate this part, that is from 1, 1 to 0, 0. So C2 I am taking here. C2 is along y equal to x from 1, 1 to 0, 0. The line integral is equals to. So y equal to x here 1, 1 to 0, 0. 1, 1 to 0, 0. So here y equal to x is a curve C2. So here the points are 1, 1 to 0, 0. So that means x and y value. So x limits are 1 to 0 and y limits also 1 to y equal to 0 we have to take. So here that's why we are taking here integral 1 to 0 x into y is, what is the y value here? In the before C1 curve, we are having y equal to x square. That's why we replaced x square. Now we are having y equal to x only. So y into, in place of y, I am replacing x plus y square. That means x square into dx plus x square into dy value. So here y equal to x. So dy equal to derivative x is 1. So dx. So in place of dy we can write the dx. Now x square plus x square. So x square plus x square into dx. So this is x square plus x square. How much here? Integral 1 to 0. X square plus x square is 2x square dx plus here x square. X square into 1 dx. So that is x square dx. So finally this is integral 1 to 0 3x square dx. 3x square dx. Now I am going to calculate this value integral 1 to 0. 3 is the constant, integral x square dx. So now 3 is the constant, integral x square is x cube by 3, x cube by 3 here. Limits are 1 to 0. Now 3 will be cancelled. Now we are going to replace the limits here. Upper limit is 0 cube minus 1 cube. So finally value is minus 1. This is minus 1. So what is the value we got now? This is along C2. Along C2 xy plus y square into dx plus x square into dy. Value is minus 1. Minus 1. This is minus 1. Now I am going to calculate total value, that is then the required line integral. What is the required line integral? Integral over C1 xy plus y square into dx plus x square. This is the first one along C1. This is the second one along C2. So we are going to add these two. That is the total required line integral. So 1 plus 2. 1 plus 2 we are doing here. So 1. For the along curve C1 I got 19 by 20 plus along the curve C2 I got here minus 1. So finally 19 by 20 minus 1. So 19 minus 20 by 20 is equal to minus 1 by 20. So this is the total line integral. So that is LHS value. LHS value I got minus 1 by 20. So only one part. So LHS part is completed. So for the verification, we need to calculate for the RHS part also. Then we can show that LHS equal to RHS to verify the grades there. Now this is our verification. Verification I am doing now. So this is RHS part. RHS part. So according to the Green's theorem, the statement. So integral pi dx or m dx plus n dy or psi dy is equal to double integral over r dou n by dou x minus dou m by dou y into dx dy. Here in place of n we are having psi, in place of n we are having pi. So now according to this we are doing here double integral over r dou psi by dou x minus dou pi by dou y. Otherwise dou n by dou x minus dou m by dou y into dx dy. So here in place of n what we are having, in place of m what we are having, we are going to see now. So what is the m value here? M equal to xy plus y square m dx, right? So what is the n value? N value is x square. So here xy m equal to xy plus y square and n equal to x square. These are the values you know. So we should know about the dou m by dou y and dou n by dou x. If you know these two values, we can integrate the final value. So here dou m by dou y means we are doing the partial differentiation with respect to y. So here when you are doing with respect to y, x is the constant. So derivative of y is 1 plus here derivative of 2y square is 2y. So finally this is x plus 2y. Dou m by dou y value is x plus 2y. Now I am doing dou n by dou x with respect to x. So here x square. So this is 2x. So dou n by dou x value is 2x and dou m by dou y value is 2y. So here we are doing here. So dou by dou x of that is dou n by dou x value is 2x. So here double integral over R 2x. Next minus dou m by dou y value minus x, minus of here we can observe x plus 2y into dx dy into dx dy. So finally this is double integral over R 2x minus x minus 2y, 2x minus x minus 2y dx dy, dx dy. Now double integral over R 2x minus x is x minus 2y into dx dy, dx dy. So now I got the value here x minus 2y into dx dy. That is the final value. If you are after doing these procedure, then only we can get this value. Directly we can't get. So that's why first we have to know about the dou m by dou x and dou n by dou x value, and we can simplify to get the final value to integrate the function. So this final value is double integral over R x minus 2y into dx dy. This is only we got here. And next important point is what are the limits of x and what are the limits of y. So here what are the x limits and what are the y limits we are going to see now. So we are taking along these two curves. So y equal to x square and y equal to x. So now y limits are here we can take y is starting here y square, y equal to x square to x. So that's why y limits are x square to x we can take, because curve is starting from here and after that ending here. So according to that we can take y equal to x square to y equal to x. And what about the x limits? X limits are 0 to 1 according to the intersecting point. Already I discussed in the before step. So from these limits we are going to replace here integral over 0 to 1 into dx integral y equal to x square to x, x minus 2y into dy, x minus 2y into dy. So now we are simplifying this one, integral 0 to 1, those are the x limits, and integral x square to x. So x minus 2y, x minus 2y, x minus 2y into dy value. What is the dy value? How we can get? Already I told you about that. So we can replace the value here dy equal to x into dx. Based on that we are replacing the value here. We got integral 0 to 1. So first we will do with respect to dy, after then we can convert into x. So here observe this carefully, integral 0 to 1 dx as it is. Now I am doing with respect to dy. So x is the constant, integral dy is y, limits are x square to x minus 2 into integral y is y square by 2, limits minus 2 into integral y dy. I can write one more step here to get the better understanding of this step. Here individually integral 0 to 1 dx, and here integral x square to x dy minus 2 integral x square to x y dy. Now we are doing here integral 0 to 1 into dx. So in x is the constant, integral dy is y minus here integral y is y square by 2, limits are x square to x. So 2 will be cancelled here. So integral 0 to 1 into dx, and here x into y limits are x square minus x minus here x square minus x whole square. So after simplification we got the value here x power 4 minus x cube into dx. So here I can do the integration for the x value. So integral 0 to 1 x power 4 dx minus integral 0 to 1 x cube dx. So here integral x power 4 is x power 5 by 5 according to the formula x power n plus 1 by n plus 1 minus here integral x cube is x power 4 by 4. Limits are 0 to 1. Limits are 0 to 1. Now we are replacing here 1 by 5. That means 1 minus 0. Here 1 by 5 is the constant. Limits are upper limit minus lower limit. Minus 1 by 4 upper limit minus lower limit. So finally this value is 1 by 5 minus 1 by 4. So this is 20. So 4 minus 5. This is minus 1 by 20. So in the previous one is when we done here for the LHS part. So we got the value minus 1 by 20. Here RHS part also we got the value minus 1 by 20. So that means LHS is equal to RHS. What is the LHS? We calculate the integral value along the curves. That means line integral. So here we calculate the surface integral also. So here both these two values are equal. That means according to the statement of the Green's theorem, this value is minus 1 by 20 and this value also minus 1 by 20. So hence we can say that Green's theorem is verified. Green's theorem is verified. So when we can say that Green's theorem is verified, if LHS equal to RHS, that means this line integral value we calculated that value and this double integral value both are same. So hence we can say that Green's theorem is verified. I hope you got the clarity about this problem. So to get the better understanding about this type of model, I am moving to one more problem. We can observe here. Verify Green's theorem. Verify Green's theorem in a plane for integral over c 3x square minus 8y square into dx plus 4y minus 6xy into dy, where c is the boundary of the region. Boundary of the region defined by what is that? Y equal to root x and y equal to x square. So here what is the y value? They given bounded by y equal to root x and y equal to x square. So from this I can write y square equal to x. So when I am doing squaring on both sides, I can write this one as a y square equal to x and y equal to x square. So nothing but sometimes they will give in the problem like this also. In place of y equal to root x, you can write y square equal to x also. Now write down the given data first. What is the given data in the problem? So given that. So here what they given? C is the boundary of the region bounded by y equal to root x and y equal to x square. Y equal to root x and y equal to x square. So we are going to integrate this value by using the Green's theorem. So like previous problem. So we have to show here also LHS part and RHS part. So first of all, we should know about the curves y equal to root x and y equal to x square. So already I told you the y equal to root x means we can write y square equal to x and here y equal to x square. So I am going to draw the one figure. So based on this curves to get the better clarity. So here I am taking y-axis and here x-axis. So now y equal to x square. Otherwise x square equal to y curve is like this. This is x square equal to y curve. Next, y square equal to x. This is the curve y square equal to x. So this is the region. This is the region, bounded region by the curves. So this is our region we are taking here. So according to that, here intersecting point is 0, 0. So what is this intersecting point? We are going to see now. Here x square equal to y and y square equal to x. So here based on that I can write y equal to root x and y equal to x square. So root x equal to x square. So x square minus root x equal to 0. Here same x into, here when you are taking the common here, x minus equal to 0. So x equal to 0 and x equal to 1. So if x equal to 0, we are getting the y value also 0. If x equal to 1, y also 1. So now we are getting the intersecting point same as like the previous problem. So this is 1 comma 1, 1 comma 1. So now what is the statement of the Green's theorem? Otherwise, how we can calculate by using the Green's theorem? Here using Green's theorem, what is the statement? Integral over c pi dx plus psi dy. That means m dx plus n dy. Otherwise, you can take capital P into dx plus capital Q into dy. These three notations are same, there is no difference. Sometimes you may get confusion about these notations. If they given pi and psi also, if they given m and n also, if they given capital P and capital Q also, there is no difference, both are same. So that you have to remember, in place of m you are having pi, in place of n you are having psi. Okay, so according to that, here dou n by dou x minus dou m by dou y into dx dy into dx dy. Now I am going to calculate the RHS part, that is RHS part. Integral over c 3x square minus 8y square into dx plus 4y minus 6y into dy is equal to. So first of all, what is the m value? M value is 3x square minus 8y square. What is the n value here? N is equal to 4y minus 6xy. 4y minus 6xy. So now I am going to calculate dou m by dou y. Dou m by dou y with respect to y I am doing here. 3 and x square both are constants. So here this value is 0 minus 8. It is the constant partial differentiation with respect to y here. So y square is 2y. So this is minus 16y. Minus 16y. This is the value of dou m by dou y. And I am calculating dou n by dou x. What is the dou n by dou x? Now I am doing with respect to x. So 4 is the constant, y is the constant. This is 0. Minus 6 into y. 6 into y. And derivative of x is 1. So this value is minus 6y. Minus 6y. This is the dou m by dou y and dou n by dou x. Now this is double integral. Dou m by dou n by dou x is minus 6y. Minus 6y. Minus dou m by dou y is minus 16y into dx dy. Dx dy. So double integral over minus 6y plus 16y. Minus 6y plus 16y dx dy. So here minus 6y plus 16y is nothing but 10y into dx dy. 10y into dx dy. So this is the value, 10y into dx dy. So now we are going to simplify now. So if you want to evaluate this integral, we should know about the limits of x and y. So now this one, double integral 10y into dx dy. So what are the y limits and what are the x limits? So here starting, you can observe y limits are 10 integral y into dx dy. So here from the figure, so this is x square equal to y. This is y equal to y square equal to x. So this is 0 comma 0 and this intersection point is 1 comma 1. Now, so here y value is here. This curve is y equal to x square. You should remember carefully. This curve is y equal to x square from starting here. So y limits are x square to y equal to, this curve is y square equal to x. This square is y square equal to x means y equal to root x. So y is equal to x square to y equal to root x. These are the y limits. And according to the intersection points, you can tell about the x limits also. X equal to 0 to x equal to 1. X equal to 0 to x equal to 1. Now I am replacing here y limits are x square to root x. X square to root x. X limits are 0 to 1. X limits are 0 to 1 here. So now this is 10 integral over 0 to 1 and here x square to root x y dy into dx. That means first we will do with respect to y, after then with respect to x. Now 10 is the constant, integral 0 to 1, integral y dy. Integral y dy is y square by 2. Integral y dy is y square by 2. Limits are x square to root x into dx. X square to root x into dx. Now 10 by 2 is the constant. Integral 0 to 1 y square. In place of y square, we are going to replace the limits now. So root x whole square minus x square whole square. So that is root x whole square means x. X square whole square means x power 4 into dx. Now from this step, I am doing 10 by 2 is 5. So write integral 0 to 1 x dx minus integral x power 4 into dx. Limits are 0 to 1. So now we are going to calculate this one. So 5 integral x is x square by 2. Limits are 0 to 1 minus integral x power 4 is x power 5 by 5. Limits are 0 to 1. So here 5 by 2 into x square, that is 1 minus 0. So first value is 5 by 2. Next one is minus 1 by 5 into 1 minus 0. So this is 1 by 5. So 5 into 1 by 2 minus 1 by 5. So finally this value I got 3 by 2. This is the RHS part. RHS equal to 3 by 2. 3 by 2. Now I am going to verify Lagrange's theorem by evaluating line integral also. So line integral means I have to calculate along the curve C1 and C2. I can add these both to get the verification for the RHS part. So that's why first I am taking the line integral along curve C. So here along curve C1 I am taking. So line integral along C1 is y equal to x square from O to A. A means here we are taking as A. So this is the point O. This is the point O. This is the point A. So from O to A. So this is along curve C1. Now along the curve C2 I am calculating, that is y equal to root x from A to O. So from this is the closed curve like this, right? So this is the C1 and starting from here to ending here close. So this is the value. So along C1 and along C2 here. So along C1 y equal to x square, along C2 y equal to root x. Now that means I am taking this value as I1 and this value is I2. So finally I can calculate I equal to I1 plus I2. That value should be equal to 3 by 2. That value should be equal to 3 by 2. Then we can verify this there. So now first I am calculating I1. I1 is nothing but along curve C1. Along curve C1, that is y equal to x square. Along the curve C1 y equal to x square. So dy equal to x to x into dx. What about the limits? X limits are 0 to 1. X limits are 0 to 1 according to the figure. Now here, what is the integral value? What is the integral value here? 3x square minus 8y square. What is this? 3x square minus 8y square into dx plus 4y minus 6xy into dy. 4y minus 6xy into dy. This value we are going to evaluate by using along the curve C1 and along the curve C2. So here 3x square and all y terms we are going to convert into x terms here. So 3x square as it is 8. If y square, so y equal to x square in place of y square, that we are replacing x power 4 into dx plus 4 into in place of y x square minus 6x into y equal to x square dy. dy is nothing but 2x into dx and x limits are 0 to 1. That is only we replaced here. X equal to 0 to 1, 3x square here 8x power 4 into dx plus 4x square minus 6x into x square into 2x dx. So here integral, we are simplifying this one, integral 0 to 1, 3x square minus 8x power 4 plus 4x square minus 6 into 2 is 12. 4x square minus, this is dy. dy value is 2x into dx, right? So 4x square into 2x dx. 4 2s are 8. 8 x square into x is x cube into dx minus 6 2s are 12. 12. So x into x square is x cube into x is x power 4. So minus 12 x power 4 into dx. According to that, we are simplifying here. So 3x cube. So 3x cube and 8x cube minus 20x power 4. So when you are simplifying this, integral 0 to 1, 3 is the constant, integral x cube value. So 3 is the constant, integral x cube is x power 4 by 4. Otherwise, we can add these two to get the integration also. So if you want, we can do the separately. Integral 0 to 1 plus 8 into integral x cube dx is x power 4 by 4. Limits are 0 to 1 minus 20 into integral x power 4 is x power 5 by 5. Limits are 0 to 1. So when you are substituting this value, we are getting here minus 1. That means I1 is along curve y equal to x square. We got I1 is minus 1. This is the 1. Now I am going to calculate along I2. Along I2 means along y equal to x. If y equal to x, what about the dy value? dy value is dx. X derivative is 1 and dx. So in place of y, we have to replace x and x limits are now according to that already I explained here when you are starting from here. So 1 to 0 limits will be there. So here integral 1 to 0 and we have to replace y value is x and dy equal to dx. So I2 equal to integral 1 to 0 3x square minus 8. In place of y square we are replacing x. So this is root x, right? So we are getting here 8x into dx plus 4 into y equal to root x. That means we can write root x equal to x power 1 by 2 also. That is only the given here. 4x power 1 by 2 minus 6 into x power 3 by 2 into here y equal to x, then we are getting dy equal to dx. But here if y equal to root x, here 1 by 2 root x into dx. 2 root x into dx. That value we are replacing here 1 by 2 root x into dx. So when you are simplifying this value, we are getting here integral 1 to 0 3x square minus 11x plus 2 into dx. So 3 is the constant, taking out integral x square dx minus 11 integral x dx plus 2 integral dx. So 3 integral x square dx means 3 into, this is 3 into x cube by 3. X cube by 3 limits are 1 to 0. Minus 11 into integral x dx is x square by 2. Limits are 1 to 0. Plus 2 into integral dx is x. Limits are 1 to 0. When you are simplifying this, we are getting the value like this. Finally, I2 equal to, we got here 5 by 2. So I1 value is minus 1. I1 value is minus 1. I2 value is 5 by 2. Now we are going to do I1 plus I2. That is minus 1 plus 5 by 2 is nothing but 3 by 2. So this is LHS. This is LHS. So LHS value we got 3 by 2. What about the RHS value? The RHS value also we got 3 by 2. So both values are equal here. So LHS is equal to RHS. LHS is equal to RHS. So hence we can say that the Green's theorem is verified. So this is the way we can calculate to verify the Green's theorem. So that means we have to do the two parts. One part is for the line integral. We will have to calculate along the curves based on the given problem, and after that we have to evaluate the double integral also. Then LHS should be equal to RHS. Then we can say that Green's theorem is verified. I hope you got the clarity about this verification of the Green's theorem. So these are the references I used in the problem. So these are the textbooks I referred to take the problems. So engineering mathematics textbook written by I.K. Iyengar, and engineering mathematics textbook written by B.S. Raval also, and you can refer B.V. Ramana also, and one more textbook you can take for the better clarity about these problems. So you can check these YouTube links or study material also you can use to get the better clarity about the verification of Green's theorem. So this is the very simple problems, and we can do the problems very well if you know the statement and if you know the how to calculate the line integral along the curve. That should you have the clarity and you should have the knowledge about the line integral, then only you can calculate along the curve C1 and along the curve C2. And one more important point, you should know about the integration formulas, then we can integrate the given line integral. If we don't know the formulas, we can't get the value here. So that's why please go through these references, and you can get the better clarity about the remaining problems also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.